So welcome for the first meeting in this part of this academic year. I'm really happy that we convened in a reasonable amount of people. And more than that, I'm very happy that we have here again Tom Kocmi. I think we thought it was a shorter time that we didn't see you, but you said it is just 2 years. So I think it's quite a long time, actually. So welcome. And we can start right now with his talk, please.
Thank you. Hello, everyone. So I'm really happy to be here. So I left 4 years ago to Microsoft, and I've been here presenting 2 years ago. But yeah, I was just saying earlier that the time flies super fast. So it feels like a year ago, but it's actually a long time. So today I'm gonna be talking about the evaluation of machine translation. So maybe for those who don't know me, I'm a researcher at Microsoft Translator, where basically I'm taking care of the whole evaluation pipeline. So from preparing the test sets, running the human evaluation, basically designing the protocols for human evaluation for the automatic evaluation, and how to decide if you have a new model, if the model is actually better. And it's really exciting topic, and I hope I will also excite you for the evaluation, because like without the good evaluation, you will be deploying bad models, papers. You will be hard to see if the papers are actually solid enough or if it's not or so. So today I'm going to be talking about the work which I did with Willem Zohar, Christian Federman, and Matt Post. And the work is called Navigating the Metric Maze, Reconciling Score, Magnitudes, and Accuracies. And the outline will be, I'll start with the motivation to a little bit explain why is it important topic and why you should know about it. Then I will talk about the approach, what we tried, talk a little bit about the estimated accuracies or thresholds. I will get to that later. And at the end, I will talk about the ablation study and like which factors affect the study. And just let me start with the motivation too, so everyone knows on the same point. So basically, if you're a reviewer and you're reading a paper, how you can know if it's really better? Or if at my place, a colleague will send me a model and it shows me some numbers, and is it good enough? Is it large enough? So oftentimes in the papers, the authors will choose the metrics. So one potential problem we are running as a field is the metric hacking, when you basically choose the metric that you like. But let's say that they run a couple of metrics and you do not have the metric that you know. Let's say that we can have some intuition to some metrics, despite I'm not that sure about that, but let's say that you see this table. Would you say that this is actually, so if you have the WMT winner and then the improved model, is it large enough improvements? Is it solid? So it's like half point comet KV 22, 1.5 for comet KV XXL, and X comet 2.33. 2.33, that's large enough. By the way, this is a solid work and it's a good. I'm just showing it for example. But if you see it and you don't know what's happening, like, are there large enough improvements? Because maybe that doesn't actually mean much. And then you have another option. Let's say that you have a paper, or again, your system, you develop a system, you have a couple of metrics, you look at them and then see, well, most of them agree, but then there is one that's completely disagreeing, and it disagrees by large, like 3.75 degradation on one, like in this case on a black. Would you go ahead with this? Do you actually improve with these techniques over the baseline or not? And how to decide on that? Is the improvements 3.75 bigger, or the others are more meaningful? So what we've been seeing in the papers oftentimes is just like authors are taking all the metrics as uniformly. So what's the largest number? Well, 3.75 is the largest, so it's the gradation. But does it mean that you can use them on the same scale? And that's basically the whole point of this of my work. So I will be discussing how much the effect size or the difference between two systems affect the reliability, how much you can actually trust the improvements, and if some metrics behave way differently. So basically, the motivation is to build some kind of rule of thumbs. So In the past, we've been thinking about like having +1 BLEU was solid enough improvements, which kind of meant that we can publish, we can deploy, etc. So can we do something in this vein? So there is a lot of work why you should not be using +1 BLEU. So I'm just like trying to motivate about like having some intuition how the metrics work. And basically, now we are getting the new metrics, but there is still, and they are way better than BLEU. But BLEU is still kind of dominant, and like they are like the inertia in the field and the lack of interpretability are the 2 points that are blocking to go ahead with the metrics that work better, but we just don't know how they behave. And this is what example what I was telling you earlier. So those are the WMT22 numbers. All the metrics in this work are multiplied by 100. So BLEU is 0 to 100, Comet 0 to 100. Basically, all the metrics are in this range, although Comet can be -infinity to +infinity, but I'm not going to go into those details. So if you plot all the system pairs, so each dot is one system pair in WMT, you can see like where they are spread across the scale. And this is the pairwise system level delta, or the difference between the two systems. So let's start with BLEU. So black line, this is the median and variance of the systems in the evolution. So for WMT, for the BLEU, the systems are about, I don't know, 3, 4 BLEU points. And that's roughly like where they on average they are behaving. But some of them are way different. You get like plus, I don't know, 17. Or like the difference is 17 points. But some other metrics, for example, Comet 20, use way wider dynamic scale of the metrics. And on the other hand, Comet 22 is using way shorter, and Comet Kiwi is 0.3. So basically, all the scores you get from Comet 21 QE will be somewhere in between range 0.03 to 0.06, if I remember correctly, after the multiplication of by 100. So the raw scores are like with a couple of zeros. And now if you would take all these metrics and say like +1 is meaningful across all of them, you will basically give credits to the authors who are using Comet 20, because getting +1 on a metric that's using way wider scale is way easier than on a metric that will never give you +1. So that's the issue. And oh yeah, so this is what I've been talking about. And one more motivation. So why can't we just like simply normalize everything towards BLEU? Let's assume that we know about BLEU. The problem is that the BLEU itself is not reliable nowadays, especially with the recent large language models. BLEU is actually quite useless, but even with NMT, it starts to be problematic. And if you would try to normalize it towards BLEU, you would also try to normalize it somehow towards the accuracy, which we actually want the better accuracy of the better metrics. And in this example, I was just showing that for each individual system pair, you get you can like all of the deltas can agree, but sometimes like some metrics will agree with the humans, and the black ones some will just disagree, and that's going towards basically the accuracy of the metrics. So ever since I think since 2016, and then we know that the BLEU is not the best performing metric. Then in 2021, I published a paper on gigantic internal test set showing that the pairwise accuracy, basically, if you have two systems and you are trying to decide which one is better without looking at the difference, the Comet and Comet Kiwi, these are 20 versions, have about like 83% accuracy to be correctly deciding. And we are talking about even small improvements or large, which is basically taking everything into consideration. While BLEU is somewhere about 74. And in last year, Markus Freitag's evaluation, they did slightly, they also look at segment level correlation, etc. BLEU is somewhere over there at the bottom, and you have basically a huge plethora of metrics that are way better than BLEU. So how can we use the better metrics and still have some intuition about how they are working? And to solve this issue, and this is the sneak peek of the final, what basically we showed in the work, is we can look at the individual accuracy per different delta. So let's say that you want, so you will get some result plus, let's say that you got for BLEU, you got plus 1 BLEU improvements. How accurate is this plus 1? And on the internal test set of 6,000 system pairs, it's roughly 65%. By the way, 50% is the toss of a coin. So if you get plus 1 on the recent systems on BLEU, it's not that reliable. And then, of course, to get 80%, you need like 2.3 BLEU. And for some other metrics, for example, the Comet Kiwi, the 1 BLEU is basically same as 0.24. And the Comet 21, the one that I've been showing with the smaller differences, 0.019. Everything after multiplication of by 100. So I will get to the table, explain it a little bit more, how we get to those numbers. So this is the intuition. Basically, we are trying to create some intuition behind the metric deltas, and then map it to the expected accuracies on how humans would roughly decide if the system is better or not, if the metrics can agree on a given effect size or the delta of the metric. And let's go to the approach. So the whole evaluation is built on an internal test set. Unfortunately, we cannot release it. So the evaluation is not replicable, but we will show later in the work on WMT that the results we came up, the table showed earlier, holds on the WMT data, and that can be replicatable. So on the internal test set, it's basically improvement of the 2021 test set. We get to 6,500 system pairs. So we have basically this work is only doable just because the sheer volume of all the systems we ever evaluated. So these are the systems since I think the cutoff is 2019. So since 2019 up to this date, basically all the humans we've been all the models we've been deploying, we've been running also human evaluation. And then now I took all the human evaluations, run the automatic scores, and evaluated how reliable they are for the given deltas. As for the segments, this is it's about 3 million human labeled segments, number of systems. It's about 94 languages, and there is about more than 10 domains, less than 20. Yes. After. Yes, exactly. Yeah, that's a good point. So, there are some reasons for the 2019, but we basically wanted the fresher systems. Later, I will also show the difference between the last 2 years and the earliers, which are way more affected by the recent models. There are also some large language models in the evaluation, but it's in the pile. So I can't say like much details about the given systems. It's just like so if the researcher in our team have a system they want to deploy, or they want to just run human evaluation for paper, we run the human evaluation, and then I just took the whole pile. So I don't have the details about the systems, but I know there are there is definitely at least 100 large language models evaluated. There could be much more. I just know about one big campaign we run. Okay, so that's for the test set on which it is. So we will show the accuracy thresholds on the internal test set, and then we will show it on WMT data to validate the results. And then how we can measure. So basically earlier, all the works you could see and the two tables comparing the different metrics is done by a pairwise accuracy approach, where basically you take all the systems in the evaluation, and then you just ask how many systems agree with the humans. And just to explain this table, on the x-axis, you have, in this case, BLEU. So those are the systems pair that had like, so for example, let's say this is a system pair that had about 15 BLEU points difference, and humans had, I don't know, +5 direct assessment score. And the pairwise accuracy basically just calculates how many systems the humans agree with metrics. So basically, both of them showed like system A is better, system B is better, in contrast all the systems. So basically trying to penalize the metric for showing opposite direction than the humans. But in this evaluation, we never look into the actual deltas. So in this pile, like about 4,000 systems are here. And just because you see one dot here doesn't mean that it's that impactful. So most of the systems will be around like the smaller deltas, and that's where the most interesting parts are coming from, results, etc. And so the difference what we are doing in our work is basically, let's take only the systems with a given delta, and then see what would be the accuracy. So basically taking this pile in contrast to this. One point is also that the table can be just swapped, because like you can always swap the systems, make it so for we don't care about like if it's +5 or -5, because you can always switch if it's system A or system B. So we just normalize this everything to the positive values. But that's more a technical detail of the evolution. And this is this is how it looks if you plot everything. So here on the table, on the x-axis, you can see the difference, the delta in the BLEU, and that's +1 BLEU, +2, 3, 4, 5. And on the y-axis, you can see the accuracy of the human evaluation. So each point in this table is calculated by 300 system pairs that have roughly this given delta. So basically, out of the data, all the data across all of the languages, I took just these systems that at the end get the two BLEU points, 1 BLEU points, and then just calculated how humans would agree. And here you can see the curve. So for +1, you get around like those 65 pairwise accuracy. Then it will grow. You about 2 points, you get towards 80. It will grow farther, but it will never cross 90% accuracy with the humans. And this is like one of the bigger problems with BLEU. It's like it's not reliable nowadays. And with actually what we saw with large language models, the BLEU is not correlating at all. Just because humans produce translationese, LLMs produce natively sounding fluent text. So we are getting to this problem that the BLEU actually cannot evaluate even a good translation. Okay, so second caveat of one caveat of this work is that we have only 6,000 systems. It's a gigantic number, but it's still kind of sparse. So when we want to take the 300 systems, we actually need to take some kind of like some epsilon around the given delta. And and here on the BLEU curve, which has a scale on the right, you basically see how wide is the bucket. So let's say the example for the 3 BLEU points. The 3 BLEU points is about 0.5 metric delta. So the bucket is roughly this wide. That's those 0.5 metric delta. Why I'm showing it is that basically we have enough system for the small deltas, or I would say like the most representative deltas, like up to 3 BLEU points, maybe up to 5 points. But then there is not that many systems that had like +20 BLEU. That's not naturally happening. So that's anytime you will see like the end of the table, just be careful about like this could be actually problem of the distribution of the systems, just because there is oftentimes something weird if you see +20 BLEU. So that's just like talking about the detail, and that's this part of the curve. Yes, so basically, for this point, it was calculated with 1.5 bucket delta. So that would be basically all the systems in this range. So from 5.25 to 6.75. So it's still like kind of reasonable, I would say, like at the end, but just like mentioning that this is the issue we have with the evaluation. Luckily, we rarely see that large differences in the system, so hopefully it will not affect it that much. And then, so since the evaluation is done on the actual data, it's noisy, and we need to somehow represent it in more smoother way, because if we would be using the original curve, then you would get a drop of the accuracy with increasing the delta, and that's something that's likely not reasonable, and it's just because of the way the humans are noisy. There is a lot of factors that affect it. So what we did is basically fit a sigmoid curve through all the data. And the reason for the sigmoid sigmoid function. It's arbitrary function, but what we wanted is, so first of all, it kind of fits the data. When you see all the other, it will not have this bump down. But the more nicer part is that sigmoid has an upper limit to some point. So we actually never will cross a threshold of 100, because even if someone would have, I don't know, plus 50 BLEU, it will still be somehow limited, bounded. And now let's go to the accuracies. So I will stress again. So when the final accuracy we take on this fitted curve, not on the actual fluctuating curve we measured. Okay, so estimated accuracies and the thresholds. So this is how it looks like for all the metrics we evaluated. I think we evaluated maybe 2 more. I did not fit into the slide. And it's how it behaves for BLEU, character F, up to Comet, BLERT 20, SP BLEU, etc. Yeah. So one interesting part to notice is that basically some metrics will never cross the 90% accuracy. It's like for the BLEU, for the character F only barely match it. SP BLEU is the same. So all the string metrics are not as reliable. While on the other hand, you have metrics that actually with large enough delta, you get close to 100. If you measure a large enough difference, humans almost always agree with them. So it's not the problem of the evaluation or of the human, like all the problematic factors that could affect it from human evaluation, the tests that we use, the systems, etc. It's actually the metric is not as reliable. And the fluctuation are done due to the empirical data that we are using. I've been looking into, well, basically I've been looking into this dip. If there is some feature like in the systems, like language or something, there doesn't seem to be anything particular. So I would assume that it could be noise from something that we don't know why. I don't think that this dip, which is in most of the metrics, is a problem of the metrics themselves. And basically, this is the table I showed earlier. So now you can know how we calculated it. So we for each of the sigmoid functions, we basically ask where it will get 65%, where it will get 80%, when it will get 95%. Here you can see that some metrics will never reach the 95%. So you never can get that accurate, but others will actually get that high. And why this table is so useful? So if you remember the tables earlier that had different deltas, one had, I don't have the table here. So that the one had like +2, there was plus 0.5, etc. What you can do is basically map those different deltas to the same space of the expected accuracy, and then see which of these actually result into largest, are most accurate, you can rely the most. So if it's because what you can see is actually that 0.5 Comet Kiwi is more reliable than 1 point of BLEU, and 0.041 Comet 20 QE is as reliable as 2.38 for BLEU. I will make one huge disclaimer and about this work. So please don't use this as a rule of thumb. This should be used in a way to build some intuition, because the metrics, like, they behave differently. We need to know somehow what to expect from it. But there is so many factors that affect it, the given evaluation. And I hope no one will ever use this work in the way that, oh, if the paper I'm reviewing will not cross at least 80%, I will reject it. That's not true. Like you can actually get, like, even in the 65%, 15, there is still more systems being accepted by the metrics and agreeing with humans than with a random toss. So just, it should be used as some kind of intuition into how the different metrics work. Each of them has the different scale, but should not be used just like, let's set a threshold. By the way, the same, it basically goes with the statistical significant testing. One of the biggest disclaimers is never use 0.05 p-value as the threshold for like cutoff. There is more into the evaluation going. So I feel that this needs to be stressed a lot. And now let's go to the, give me a sec, please. So now I've been talking about the thresholds and how they look like, how they can compare. But is it actually that reliable? What are the factors that affect it? And can I show you on different tests that it actually works, or if it's just on the internal one? So in this study, in this analysis, we will look at various factors that can affect the difference between two systems. And that's one of them is different domains and different test set. Maybe the accuracies as calculated are just a fragment of our internal test sets and domains. Second could be language pair. For some languages, it could just metrics could be more reliable on different languages, etc. Or alternatively, it could be that, let's say, I think like Chinese, Japanese, Korean, this group will have will need much larger deltas or much more smaller. Maybe it's actually heavily affected by the language pair. We will also look at the system types, how the actual underlying system the pair affects. And here we look into two sets, if the systems are similar or if they are completely different. And the last one is the test set size. Does the size of the test set affect? Because will it hold for 500 sentences? Will it hold for 2,000 sentences? Internally, our test set have 30,000 sentences. So will it hold in this way? And so let's go to the evaluation. So let's start with the different domain and a test set. So this is the evaluation I mentioned earlier, is basically, so we build the thresholds based on the internal data set. Now let's see how they would work on the WMT 22 and 23. And if they work, like if they can result in, if they show that what we did is correct. Here we put together WMT 22 and WMT 23. The reason is that publicly available, there is a little human evaluated publicly available data. So even to run this evaluation where basically each point was 300 systems, and that's just, the sheer volume is a little bit limited. So that's why we combined these two. We used only the source-based direct assessment and MQM in combination. So we did not use the reference-based direct assessment done on MT Turks that been criticized at WMT in the past. And we basically plotted. And let me explain the graph before going, just what this shows. So what we did is for each system pair, we would be calculating the estimated accuracy. And then for the same pair, we look how the WMT data, the humans from WMT would mesh it. And that, let's call it the real accuracy on WMT data. So basically what we did the same way, again, aggregating the systems together, is let's take these systems, see what would be for their delta. Let's say that one system would have 0.5 BLEU difference, and that would be, I don't know, 60% accuracy. What accuracy would be in the real data? And they've been calculated on the humans from WMT. This is different set of domains. This is a different test set. We do not use WMT. These test sets are not in the internal evaluation. And what you should see here is basically, in the ideal case that there is no noise, nothing, everything is perfect, you would expect this black line. Basically, the expected accuracy would grow linearly with the real accuracies. However, there is, of course, some noise, and now it's up to us to decide how much noise is actually meaningful and how much it affects it. So let's start with, for example, the character F is a nice example. So we can see like here, it kind of fluctuates around like this, the linear graph, up to the point about 80%, and then there is this drop at the end. And this is from the tail of the data where we don't have that many system pairs. So I would not say that there is something funky happening with the metric. It's more problem of the limited data for this threshold. Just to say, like, so to get to the 90% accuracy estimated for so 85 so the 85 was 2.31 BLEU difference, which is quite large. It's not as frequently happening. So that's, I wouldn't say that there is something here. There are two metrics that, so then there is a lot of, so all the other metrics that are not listed here are somewhere in this gray around the line, which we believe that they are roughly correlating with the real numbers. There are two exceptions. One is Comet QE21, which is underperforming, and then Comet 22, which is overperforming. What does it mean? For the Comet 21, we are giving higher estimated accuracies than would be the real ones. So we are basically inflating the metric, our internal data set, like either our humans, the test set, what we measure. On those, the Comet 21 QE seems to be better than it is on WMT data, and vice versa. For Comet 22, we are giving it much higher, well, a bit higher accuracies than would be the real one. So let's say for the 70, yes, so for the 70, we could get to 75. So basically, we would so for some given delta, we would estimate it that it's 70% accuracy, while on the WMT data, it would actually get to 75. Now it's up to us, and now this is the noise that we need to work with. So is this difference meaningful? Can we somehow use these accuracies to align the metrics in a way? And I'm leaving it up to everyone if you believe in this or not. For us, we went ahead with this, and we feel that something that aligns the metrics actually is meaningful. Despite that, there will be always some noise, and we need to know that there is a noise in the data in the evaluation. Give me a second. Okay, so now let's look at different language pairs. As mentioned earlier, some languages maybe behave differently, and maybe the range that the metric is using for different metrics is different. So in this evaluation, what we did is basically splitting the test set into smaller chunks, and one of them is, so the green line is for all the languages. So this is for Comet Kiwi. So the green line is the original line you saw earlier in the slides. Then what we did the same evaluation for into English. So basically taking all the languages going to English, then English to going to all the languages, and then we separately go for Chinese Korean, Japanese Korean. It made the evaluation smaller. So into English, it's about 3,000 systems. From English, it's about 3,200 systems. For Chinese Korean, Japanese, it's nearly 1,000 systems. So that's a limitation of the evaluation. And again, the problem is the quantity of the data. However, we kind of think that for Comet Kiwi, all of them behaves kind of similarly. So there doesn't seem to be much of a difference between the different metrics and, different language pairs. So for Comet Kiwi, we don't think that the language pair affects the delta that much. However, some metrics are a bit problematic. And here, I took an example for HERT-F. In the appendix of the paper, you can see all the metrics. BLEU has the same problem. For Korean, so again, let's say for the all language into English from English, they kind of more or less behave similarly, although this is questionable. The problem is Chinese, Korean, Japanese, which again, after some point, start degrading. And here it's hard to say if it's a relic of the tail of the data that I've been mentioning earlier, because it's basically happening about the 2-3 points too, or if the metric is behaving differently. So this definitely needs much more attention to how much the language pair affects the metric. The good point is that for most metrics, especially the Comet Kiwi, BLERT, and those, they do not seem to be affected by the language pair. It's more problem with the string-based metrics that are doing some n-gram matching. Okay, so now let's go, and this is one of the interesting evaluation into what system do you compare? And here in this evaluation, we split the system into two groups. One group we called improved systems, and those are basically if you have a system, you call it baseline, and you change the data, change the architecture, but basically you do just small tweak. So they are related somehow. So they should produce similar outputs. They should behave similarly. There is just some improvement on happening. And the second group is unrelated. Those are, in our case, comparison, our Microsoft against Google or our competitors. The same is happening at WMT. WMT has a bunch of systems, each developed by different team. They are completely unrelated, and they are producing different outputs. And we look into these two groups separately to see how it behaves. And this is one of the really interesting points. So if you look for the improved systems, this is again for Kocmi. The improved systems is quite good to guess. Like, it makes sense. So the original baseline system was had some performance. You improve something, it changed few sentences, few phrases. Both metrics like it, both humans love it. It's really nice. It's not as nice for the unrelated. So when you have one system developed by team A and one system developed by team B, they produce completely different translation. And now it's hard to say which of these translation is more difficult, and which of these translation is better in this sense, if they are not related to each other. So it's more difficult for the metric to guess. But let's say for Kocmi, it still kind of holds. It grows. It's not growing that fast, and it has lower accuracies for the deltas. But then you go to BLEU. Again, improve systems, really nice. BLEU still can actually relate. If you have a baseline, you improve it. BLEU can work. You have the same system, you improve something. It's getting better. But then if you, in your work, are comparing your method to the state of the art from WMT, if you compare it to completely different team, the previous work, you get to this blue line. And for BLEU, this is actually horrible. Like, you get around 60% up to BLEU 3. And then when you finally get to BLEU 3, which is not as frequently happening, and to BLEU 4, maybe 5, you are still only about 80%. And this is the problem. And now the problem doesn't have to be just BLEU. It just, if the translation are so different, it's hard to judge which one is better if there are no clear problems. And BLEU matching it to human reference is not doing that great job. So this is one of the, I hope this will have some follow-up works and someone will pick it up, just because oftentimes in the papers you see the improvements we did over the baseline, we do ablation studies. For those, the metrics behave really nicely. And then there is the section, how we compete to state of the art, the previous work, the paper someone else published. And for those, it's difficult. And in that case, I would never trust BLEU and rather go for metrics like Kocmi. In the paper, we have all the metrics showing that the pre-trained metrics actually have this curve much nicer than metrics like BLEU, character, and those, and that. So here I would just like mention that BLEU is not as doomed as it may seem, as long as it's like for the baseline and improved system. But please don't use it for like unrelated system. It's for currently, the current MT is way over BLEU. One last asterisk for the low resource languages where the MT is still really bad. Yeah, of course, the BLEU will hold, but that's maybe the only thing. And now let's go to the last part of the evaluation, and that's the test set size. So is the number of sentences in the test set, will the number of sentences in the test set affect the delta? Will the delta change for 500 sentences, 1,000, 10,000? And for this, we just took, so this is one single system pair, system 1 and system 2. And then we just sampled from the test set. We sampled on the x-axis. Now please look just for the blue curve. For the x-axis, we sampled like 500 sentences, 1,000 sentences, 2,000, 3,000. And we calculated, I think this is the variance of the sample that we've been getting. And it does fluctuate a little bit. However, it stays consistent. So as long as the distribution of the sentences is not changing, the delta does not change that much in contrast to the test set size. However, this actually shows one thing, and that's so we also plotted the statistical significant testing, the p-value, and this has been mentioned in MT anecdotically over all the times I remember. Like there is a group of use statistical testing. There is the group that statistical testing can be cheated. So what we did is basically just for the same samples, we also calculated statistical significant testing. I think this is for Comet Kiwi, so that would be student t-test. And yes, of course, with a larger test set, the p-value will be dropping. But the p-value is dropping for different reasons. It drops because you are making the statistical test more powerful. So in no way we are saying that the p-values, the statistical significant testing is doomed and should not be used and it's bad. It's just like for our field as MT, where you can make the test set really large. It's not as it's not the only point that can help to distinguish between the two systems. And here I'm just showing a few other systems. And one is that, for example, for usually the 2000 sentences, you have the test set size of the 2000 sentences. So for this system pair, the 2000 sentences would not get 0.05 p-value, but with about like 8,000 sentences, you would cross even the 0.01 p-value. This is something that we've been running internally a lot, because when we introduced the 30,000 sentences test sets, everything was statistically significant. And it's due to this phenomena, or like not everything, all the small changes. And again, not going into details with the statistics that much, just it's not surprising. It's just like, since the testing is more powerful, it will just see the differences even much smaller. So even for 0.1 Comet Kiwi, it will show that, yeah, there is a measurable difference in the distribution. But it never answers the question, will this difference be noticed by humans? Is it large enough difference? And that's why we are proposing the threshold accuracies. And that was end of the main part. I will have just one other bonus material. So since we built already this test set and we can't release it, so what we also do is basically do the new metric share task evaluation on our internal data set and see how in the year 2023 the metrics would behave. And let's go for this column, and then like the winner in internal test set would be the Comet Kiwi, followed by Xcomet XXL, and then you go down to some SP BLEU 2200 and BLEU. And importantly, there is blurred default. And if you ever see in the paper, or if you will ever use blurred, be careful. The default implementation is using testing checkpoint, which was never meant to be used for evaluation, but is the default. If you don't change it, you get this, which is worse than BLEU. So please always change to BLEU 20. Authors say that you should do it, but just because they set it to some testing checkpoint, it could create a lot of issues in the evaluation. And here, what I'm just showing, so the first line just shows the number of systems in each evaluation. So this is the first three columns are our test set. It's compared to last year WMT metric share task pairwise accuracy. And here we did the split between the years. So 2019 to 2021 are in this column, 22 to 23 are in this column. And what's more important is that it's not that the actual accuracies would change. It's more about the order of the metrics, because the set of the systems evaluated will affect the outcome. What we notice is that despite like by a small margin on the whole test set Comet Kiwi works, which by the way is a quality estimation metric. This metric does not need any references and it's a winner. So you don't need to produce expensive test set. You can have fresh test sets, different domains, something that we really need for now LLM era, where we don't know what the LLM's been trained on. But what we notice is that maybe it gets the games from the earlier 2019-21 a little bit, while for the most recent systems, the Xcomet XXL is actually slightly better. However, from my point of view, I would say that there are not that much large differences. By the way, WMT23 shows the same. So kind of like using all of these metrics is reasonable, because all of them are like kind of there are small accuracies, while for example, for the BLEU, the drop is already quite large. So 10% accuracies, there is like in almost 15. For WMT is also 10%. So this is just which metric is the best. And I'll skip, I'll skip this one. I'll get to that maybe later. And the last point is basically we release this tool. So on this web page, or you can use it as a pip install, you can get those accuracies. So if you ever go into evaluation of the MTE systems and you have a paper, or if you are deploying it and you don't know the intuition, you can just go to our tool, click what the difference you got, and you will get first what would be the expected accuracies and what are roughly the differences you could expect for the other metrics. So hopefully this will help people, researchers, build some kind of intuition how the metrics works, and just knowing that they are behaving quite differently and we should know about that and somehow try to align them. And this is it. Thank you a lot for the attention, and I'm happy to answer any questions.
Okay.